So in this lecture, we see the topic that is cyclic groups. So first we see cyclic groups and cyclic subgroups. So definition of cyclic group. A group is said to be cyclic if there exists an element A belongs to G such that every element of G can be written as some integral power of A. So here every element of G we can write it as some integral power of A. Here A is called generator of that cyclic group. So notation, cyclic group G generated by A is denoted by this notation, that is cyclic group generated by A. That is your cyclic group generated by A can be written as it is equal to set of all A raised to n such that n belongs to Z, and that is equal to G. So here every element of G can be written as some integral power of A. Examples. So first example, that is Z with operation addition is cyclic group generated by 1, because here with respect to operation addition every element can be written as some integral power of 1. So since here every element n belongs to Z can be written as n can be written as, if n is positive, then we write 1 raised to n as equal to 1 plus 1 plus 1 n times. So this is the value of n. Whenever n is equal to 0, we write it n as equal to 1 raised to 0, that is equal to identity element, that is equal to 0. And if n is negative, then n can be written as minus 1 raised to minus n. Sorry, 1 raised to minus n. So it can be written as minus 1 plus minus 1 plus minus 1 minus n times. So this is the value of n. So n can be written as integral power of 1. So 1 is generator of this cyclic group. The next example, for n greater than 1, the group that is residue classes modulo n, that is Zn, with operation addition modulo n is cyclic group generated by 1 bar. Again here, any element that is m bar belongs to Zn, we write it as integral power of 1 bar, because 1 bar, m bar can be written as 1 bar raised to m. 1 bar raised to m is 1 bar plus 1 bar plus 1 bar m times whenever m is greater than 0. And if m is equal to 0, then 1 bar raised to 0, that we know it is identity element, with respect to addition it is 0 bar. So here this is the cyclic group generated by 1 bar. Then third and important example, consider the group G that is set containing 1 minus 1 I minus I. Under operation multiplication, it is cyclic group generated by element I, because every element of G we can write it as integral power of I. So see here, that is 1 can be written as I raised to 4, minus 1 can be written as I square, I can be written as I raised to 1, and minus I can be written as I raised to 3. So here every element of G is integral power of I. So here G is cyclic group generated by I. So here G is cyclic group generated by I, and then we write here G is equal to this notation, that is G is cyclic group generated by I. The next example, for a fixed positive integer n, group nz with operation addition is cyclic group generated by n, because every element of nz is nothing but multiple of n. So we write it as k plus k plus k n times. So it is cyclic group generated by n. Now we have next important theorem, that is prove that every cyclic group is abelian. So here we have to show every cyclic group is abelian. So let G be a cyclic group generated by A. So that is every element of G can be written as some integral power of A. So we take two elements in this cyclic group. Let x and y belongs to this G. Because this is cyclic group generated by A, x and y both are elements of integral power of A. So x can be written as a raised to r, y can be written as a raised to t for some integers r and t. Now we show this group is abelian. That is here operation multiplication is commutative. That is here we show x into y is equal to y into x. So see here, x into y we write it as a raised to r into a raised to t, or it can be written as a raised to r plus t, or it can be written as a raised to t plus r, because r and t both are integers. R plus t is equal to t plus r, and a raised to t plus r we write it as a raised to t into a raised to r. So a raised to t is y and a raised to r is x. So thus here we get x into y is equal to y into x. So this group is abelian. So here every cyclic group is abelian, but converse is not true. So here converse of our theorem is not true. That is, we have the example of abelian group which is not cyclic. So abelian group need not be cyclic. So example, consider the group Z dash with respect to operation multiplication modulo 8. So it is abelian group, but it is not cyclic, because we know that Z dash contains 4 elements, that is 1 bar, 3 bar, 5 bar, and 7 bar. So here it is not cyclic group. It is abelian group, because we know that 3 into 5 can be written as 1 into 5 into 3. 5 into 7 can be written as 7 into 5. So it is a abelian group, but it is not cyclic. That is, this group does not contain generator. Because 1 bar raised to n, if we calculate for all n belongs to Z, its value is always equal to 1 bar. Means here 1 bar is not generator of given group. That is, every element cannot be written as integral power of 1 bar. So here 1 bar is not generator. Again, we know that 3 bar raised to n is either equal to 1 bar or 3 bar, because 3 bar square is 9, modulo it is 1 bar. 3 bar cube is again 3 bar. So 3 bar raised to n is either 1 bar or 3 bar. Whatever may be value of n, whatever may be that integer. So here 3 bar is not generator of the given group. Similarly, 5 bar and 7 bar both are not generators, because 5 bar raised to n is either 1 bar or 5 bar. 7 bar raised to n is again either 1 bar or 7 bar. So here this group has no generator. So this group is not cyclic. Now next theorem, that is, if G is a cyclic group generated by A, then A inverse is also generator of that cyclic group. Means here, if the given group is cyclic group generated by any element, then its inverse is also the generator of that cyclic group. So note that any cyclic group has at least two generators, A and A inverse. So let G is the cyclic group generated by A. So every element of G can be written as some integral power of A. So here G is equal to cyclic group generated by A. That is, every element of G is integral power of A. So it is A raised to n, such that n belongs to Z. Now we have to show G is again cyclic group generated by A inverse. So clearly here cyclic group generated by A inverse is subset of G, because G is the whole group and every element belongs to G. So cyclic group generated by A inverse is subset of G. Now we show G is subset of cyclic group generated by A inverse. So take one element in G. So let Y belongs to G. But we know that here G is cyclic group generated by A. So Y can be written as some integral power of A. So here we write Y is equal to A raised to n for some integer n belongs to Z. Now we write this Y equal to A raised to n as equal to, we write this A as equal to A inverse inverse. So it is A inverse inverse raised to n, or it can be written as A inverse raised to minus n. So it is integral power of A inverse. So it belongs to cyclic group generated by A inverse. So Y belongs to that G, and Y can be belongs to cyclic group generated by A inverse. So from that we can say G is subset of cyclic group generated by A inverse. So thus here from 1 and 2 both sets are equal. That is, G is again cyclic group generated by A inverse. Hence A inverse is also generator of the cyclic group. Then we have next theorem. Let G be a group and A belongs to G. Then prove that H is equal to set of all A raised to n such that n belongs to Z is smallest subgroup of G containing A. So here H is smallest subgroup of G containing A, that we have to show. So let H is equal to set of all A raised to n such that n belongs to Z. Now A is equal to A raised to 1. So it is integral power of A, so it belongs to H. So from that we can say H is non-empty. So here H is non-empty set. So take X and Y belongs to H. So since X and Y belongs to H, so they are of this type, A raised to n. We have to show H is smallest subgroup. So first we show it is subgroup. So for X and Y belongs to H, X can be written as A raised to R, Y can be written as A raised to T for some R and T belongs to Z. Now consider X into Y inverse. So here we use that necessary and sufficient condition for inverse. So X into Y inverse is A raised to R into A raised to T inverse. It can be written as A raised to R into A raised to minus T, or it is A raised to R minus T, and that belongs to H. So thus here H is subgroup of given group G. Now we have to show H is smallest subgroup of G of this type. So I'll let K is a subgroup of G such that A belongs to K. So here we take any subgroup of G that contains A. Now we show here H is subset of K. To show H is subset of K, let X belongs to H. We show X is also element of K. So because X is element of H, it is some integral power of A. So X can be written as A raised to R for some R belongs to Z. So we know that here since K is subgroup and here X is integral power of A, so from that we can say X belongs to K. So thus here we have whenever X is element of H, we get X is element of K. So this here H is subset of K. Thus H is equal to this set, that is set of all A raised to n such that n belongs to Z is the smallest subgroup of G containing A. Now this subgroup H denoted by this notation, that is subgroup cyclic group generated by A, is called cyclic group generated by that element A. Then we have next theorem, that is in this theorem we show subgroup of cyclic group with cyclic. That is every subgroup of cyclic with cyclic. So let G be a cyclic group generated by A, and let H be subgroup of that given group G. So here G is cyclic group generated by A. So G can be written as by this notation, that is every element of G is integral power of A. Let H is subgroup of G. So if H is equal to set containing singleton E only, then in that case we can say H is cyclic group generated by E. So here H is cyclic. Suppose that H contains one more element than E. So suppose that H is not equal to singleton E. So H contains one more elements than E. So that X belongs to H such that X is not equal to E. Now X belongs to H. H is subset of G, and G is here cyclic group generated by A. So X can be written as some integral power of A. So thus X is equal to A raised to P for some integer P. P not equal to 0. Now X is equal to A raised to P for some integer P. So from that we can say X inverse is equal to A raised to minus P. X inverse is equal to A raised to P inverse, that is equal to A raised to minus P belongs to H. So here we note that either P is positive integer or minus P is positive integer. So whenever since either P or minus P is positive, so H contains at least one element of the type A raised to n where n is positive, where n is natural number. So H contains at least one element of the type A raised to n where n is positive integer, because here X is the element of H, X inverse is also element of H. So here H contains at least one element of the type A raised to n where n is positive integer. So let T be the smallest positive integer such that A raised to T belongs to H. So here we show H is cyclic group generated by A raised to T. So clearly cyclic group generated by A raised to T is subset of H. Here we show H is cyclic group generated by A raised to T. So that is H is cyclic group generated by A raised to T. So here clearly cyclic group generated by A raised to T is subset of H. Now we show H is subset of cyclic group generated by A raised to T. So let Y belongs to H. So since Y is element of H and H is subset of G, that is cyclic generated by A, so Y can be written as some integral power of A. So Y belongs to G, that is cyclic generated by A. So Y can be written as A raised to M for some M belongs to Z. So here we write this Y or A raised to M as A raised to QT. So here use division algorithm. So because M is integer here, we divide this M by T to get some quotient Q and remainder R. So by division algorithm, M can be written as Qt plus R, where 0 less than or equal to R less than T. So here R is a remainder when we divide M by T. So if R is not equal to 0, then we write A raised to R is equal to, from this value of R is M minus Qt. So A raised to R is equal to A raised to M minus Qt, or it is A raised to M into A raised to minus Qt. So if R is not equal to 0, then we have this one. So it can be written as A raised to M into A raised to T raised to minus Q. But we know that A raised to M, that is equal to Y, it belongs to H, and A raised to T is also element of H. So this product belongs to H. So here A raised to R is element of H. Therefore A raised to R belongs to H, but T is the smallest positive integer such that A raised to T belongs to H. त्याच्यामुळे इथे condition काय मिळेल आपल्याला, T is less than R. So here we get T less than or equal to R, which is not possible because R is less than T. So which is not possible as R is less than T. So therefore we get R must be equal to 0. If आपण suppose केलं तर R non-zero, then we get a contradiction. So here R must be equal to 0. So put that value in equation, this equation, and that is M is equal to Qt plus R. So R is equal to 0. So here we get M is equal to Qt. So put that value in Y. So therefore Y is equal to A raised to M, that is equal to A raised to Qt. So it is equal to A raised to T raised to Q. So that belongs to ideal generated by A raised to T. So thus here Y belongs to H and Y belongs to ideal generated by A raised to T. So from that we can say H is subset of cyclic group generated by A raised to T. So thus here we have group cyclic group generated by A raised to T is subset of H, and H is subset of cyclic group generated by A raised to T. So both are equal. So by equation 1, see the equation 1. So this is the equation number 1. Cyclic group generated by A raised to T is subset of H, and by equation 3 we get H is subset of cyclic group generated by A raised to T. So both sides are equal. So H is equal to cyclic group generated by A raised to T. So here H is also cyclic. So thus here subgroup of cyclic group is cyclic. Thank you.